The first basic sensing elements were resistive sensing elements, but there are also a large number of capacitive sensing elements. And before we go through the different elements, we have to look at the principle behind a capacitor. And capacitors, they are made of two areas, like this. So there are basically two metal plates that are close to each other. And if we look at it a bit more schematic, you can say that it's a metal plate like that, close to a metal plate like that. Now, they are usually connected in a circuit with a AC source, which means that the source has an alternating current, the current that goes back and forth. So it's connected in a circuit with a alternating current or voltage, a waveform. So the current here will go back and forth in this circuit. Now, when the current goes in one direction, you know, I guess, that the electrons go the other way around. So you will have electrons, an overrepresentation of electrons building up on one side. Now, they will chase away the electrons that were here. They will go into this. So electrons going out from this side will fill the plate on that side, the right side, and the loop is closed because you have electrons that were chased away from this side of the capacitor. Now I can write green dots here symbolizing a lack of electrons. So you have an overrepresentation of electrons here and a lack of electrons on the other side. Now, if I represent that with symbolics, I will have a negative electric field here and a positive charge. Negative charge on one side, positive on the other. Negative because I have too many electrons, and here because I lack electrons. And what make these electrons on one side chase away the ones on the other side is that you have an electric field across the gap between the capacitors. If the capacitor plates, if the plates touch, you will have a normal current flowing, but now you have a current that is driven by the electrical field. Of course, if this current here flows in this direction for a very, very long time, well, then in the end, the amount of electrons that were on this side, we are more or less running out of electrons on this side. There will be no more electrons to chase away. So for this system to work, the current will have to change direction every now and then. Now, in alternating circuits with alternating currents, you can say that the capacitor represents something called an impedance Z. So the capacitor represents some kind of resistance to the circuit. But it's a bit special, that resistance, but it is a kind of resistance, and it can be found in circuits where you have an alternating current. The size of this impedance depends on the size of the capacitor. The size of the capacitor, C, depends on three things. It's something called mu, times area over distance. The area is the size of these plates. The higher the area, the larger the plates, the larger the capacitance, or the capacity to store electrons, store charge. The area is from the size of the plates. The d is the distance between the plates. So the smaller the distance, the more effective the electrical field between them. So smaller distance would make a larger capacitor. Therefore, it belongs to the denominator. The mu is the material that we put between the two plates here. If we have vacuum, the vacuum is not a very good material to help the electrical field between the two areas. However, for example, polypropylene kind of plastic is a good material that will help the electrical field. So the mu represents what kind of material we have between the plates. Well, the electric theory behind capacitors can be a bit difficult, and it's not very important to know at this stage, to know everything about. But the thing that you must remember is that if we can manipulate the size of the capacitance, we can make a circuit where the capacitance manipulates the amount of current in the circuit. So the current in a circuit with the alternating current. So let me write that in another way. I, alternating current, is a function of the capacitance. And also, of course, then voltage in an alternating current circuit is a function of the capacitance. So, if we can manipulate the capacitance, we can measure a change in the voltage and in the current. Now, what can we do? We can do three things. We can manipulate the plate separation. We can make the plates come closer to each other and further away from each other, and that would manipulate the d in that equation. If you see the epsilon that I wrote down on the other slide, you have here epsilon naught and epsilon without a subscript to it. This is the epsilon for vacuum, and this is called the relative permeability of the material that we put between the plates. So if we only have vacuum, well, then the epsilon here goes away. If we have plastic, that would have an epsilon with a number that makes the overall epsilon higher than it used to be with vacuum. Anyways, we can manipulate the plate separation. That would be to manipulate the d. We can manipulate the effective area, which will say the area that is that contains the electrical field is the overlapping area here. So if we push this plate here sideways, that would manipulate the A. And also we can manipulate the dielectric, which means the material between the plates. We can push in some material and take material away again. That would be to manipulate the dielectric, which means to manipulate the epsilon there.